What's going on, guys? So this is my revision video for everything you need to know on electricity. The entire electricity topic will be outlined in this video. So if you're taking AS physics, this video is for you, and those of you revising for your A-level physics, this video will help you also. So everyone, I've covered it all in this video here. In this video, I'll be walking you through electricity basics, internal resistance, resistivity, and potential dividers. Everything will be outlined, including how we do the required practicals. If you don't know who I am, my name is Mr. Ceeraz. I'm a qualified physics teacher with over 500 videos on YouTube. I've worked with the BBC and ITV, creating resources to break down barriers in physics education. You can see my credentials, yes, and obviously I know it, but I made this video because I know loads of kids are struggling in physics, and it's a difficult subject, people. So that's the reason why I made this channel, and that's the reason why I made this video, so therefore you don't have to look anywhere else. You can access it all without paying anything. Obviously, you know, just drop me a like if you can, and if you get stuck on anything, just comment below and I'll do my best to solve it. If you look at my previous videos, I've got loads of stuff in detail, so this is obviously a revision video to help you before a test. This will be ideal, but if you want me to work through something and explain it in depth, check out my playlist. Just search for the video that you want. Everything's on there to help you with your studies. Okay, so let's do this, guys. Let's do this in 3, 2, 1, bang. A-level physics electricity explained in one video. Current is equal to the rate of flow of charge. Conventional current flows from the positive terminal to the negative terminal, which is the long stick to the small one. As you can see, it's going in this direction through the resistor, through the ammeter, and returning back again. The ammeter is obviously used to measure the current and is connected in series. Current is equal to charge divided by time. I is therefore equal to Q divided by T. That's the formula. In terms of the units, I is in amps, charge in coulombs, time is in seconds. Electron flow is from the negative terminal to the positive terminal, going the opposite way. The reason why is because electrons were discovered to have negative charge. Therefore, look, negative, negative, they will be repelled away and then traveling to the positive terminal, being attracted. So conventional current is not the same as the electron flow. Voltage / potential difference between 2 points. The voltage is simply going to be the energy transferred per unit of charge. V is equal to energy divided by charge, or V is equal to E over Q over here. In terms of the units, and voltage is measured in volts, energy is in joules, charge in coulombs. The best way I talk about it is going to be, imagine 1 coulomb of charge going around the circuit. It's how much energy each one is going to be carrying. So imagine they go around, they pick up some energy, a block is going to be a bit of energy, they go around and they drop it off at a component and return back again. The voltmeter measures the potential difference, or the voltage between these 2 points. It is connected in parallel around the component under test. Basically, look, upon entry, obviously you had some energy. Upon exit, you don't. It's checking out how much energy was going to be transferred per unit of charge to that component. Electron charge, number of electrons, and coulombs. So charge is going to be Q. Number of electrons is going to be N. The electron charge is going to be 1.6 times by 10 to the minus 19 coulombs. That means that if you were to be given an electron in your hand, you have gained 1.6 times by 10 to the minus 19 coulombs. That's going to be the charge of one electron. So therefore, what is inside 1 coulomb? Well, in 1 coulomb, we can see how many electrons there would be. So 1 coulomb divided by the charge of each electron, 1.6 times by 10 to the minus 19, you've got 6.2 times by 10 to the power of 18 electrons then inside 1 coulomb. So when people talk about 1 coulomb of charge, that's going to be 6.2 times by 10 to the number 18 electrons. So 6.2 times by 10 to the 18 electrons inside 1 coulomb. Kirchhoff's first law. Kirchhoff's first law talks about the current in a circuit, especially at the junctions. So basically it's going to be this: the total current into a junction, which is going to be a split, yes, in the road, yes, there's a split in the circuit, is equal to the total current out. So sigma the current in is equal to sigma the current out. So the total current in is equal to total current out at the junction over here. In this case, we can see that IT is equal to I1 plus I2, yes, and this one, they recombine. I1 plus I2 is equal to IT in this case over here. This is going to be Kirchhoff's first law. Kirchhoff's second law, the total voltage into a loop is equal to the total voltage out of the loop. So right now, the voltage behaves in the following way. So all you do is simply say that the sigma the voltage in is equal to sigma the voltage out in any loop, any complete loop here. So in this case, look, the voltage going in is equal to V1 plus V2. So look, V in is equal to V1 plus V2. But there's also, and then returning back again, then the next loop, V in is also equal to V3. Yes, so V in is also equal to V3. So therefore, in general, you could say that V in is equal to V1 plus V2, which is also equal to V3 in this case, which is going to be Kirchhoff's second law. Ohm's law. Ohm's law states that the voltage is directly proportional to current for a fixed resistor at constant temperature over here. So for example, if we were to put a fixed resistor in a simple circuit with a variable resistor, having an ammeter and a voltmeter connected around it, we'd be able to obtain the following results: that voltage is directly proportional to the current, yes, provided that the resistance is constant. So V is equal to IR. Obviously this resistor must remain constant. It's not changing. It's a fixed resistor here. The voltage is in volts, current is in amps, the resistance is in ohms. So V, A, and omega over here for the resistance. VI characteristics. If we were to do the same experiment but just replacing that fixed resistor with a filament bulb and look at how voltage and current behave in it, we can see that's the filament bulb looks like an S-shaped graph. The current stops increasing. The reason why is because as the bulb heats up, the resistance increases, and therefore there are more collisions between the electrons and the metal ions, and as they collide more often, obviously that creates the resistance, and therefore it stops the current from increasing. So we end up with this kind of S-shaped graph over here. The diode. The diode is different to the filament lamp. The diode only allows current to flow through it in one direction. So as you can see, the graph is 0 in one direction, and after a certain value it starts to go up. We can see that the reason why the current is 0 in this direction is because there is a high resistance when it's in a certain orientation. So the diode only allows current to flow through it in a certain direction, and the orientation of it matters within your circuit. Thermistor. A resistor that depends upon the temperature of the surroundings. This over here is a symbol for a thermistor, and as you can see, this is an NTC thermistor, a negative temperature coefficient thermistor. As the temperature increases, the resistance drops down. Make sure that you're familiar with this. An LDR is going to be a light dependent resistor. Here's my symbol. It has 2 rays of light going into it. A resistor which depends upon the amount of light intensity in its surroundings. This is going to be also a negative temperature coefficient LDR. As the light intensity increases, the resistance drops down. The conduction electrons inside. So why is this occurring over here? So first of all, imagine we have a box and you've got electrons which are in a semi-bound state. So right now they're in a semi-bound state. Electrons, they're not free to move, but they can move if they're given a bit of energy. If you apply some light, in this case from the LDR, or some heat from the thermistor, what happens is these electrons break free and now are able to flow. And obviously if the electrons inside are now able to flow, that will obviously reduce the resistance. Hence why for both of those graphs for the NTCs, they both drop down. Electrical power. Power is equal to the rate at which energy is transferred. It's equal to energy divided by time. Electrical power is equal to current times by the voltage. Why? Because P is equal to I times by V. Yes? And what is current? Current is Q over T. Voltage is energy per unit charge. Therefore, look, Q cancels out. It's going to be E over T. So power is E over T, which is I times by V. But we also know that components will also obey Ohm's law. We can then plug the values in of Ohm's law. V is equal to IR, substitute them into here. Power is also equal to V squared over R, because V is equal to IR. That would make it P is equal to I squared R. And if we know that I is equal to V over R, therefore it makes the top formula V squared divided by R. Voltmeters and ammeters. Ammeters have a minimal resistance to allow maximum current to flow through it. So they have a minimal resistance, that's why the current can flow through easily. Voltmeters are different. They have the maximum resistance. The reason why is because if it had a low resistance, the current wouldn't go through that component. It would bypass it, go around here and go around. So you want the maximum resistance here to force it through the component, and the minimum resistance here now enabling it to travel all the way through. Combining resistors in series and parallel. Right, so we can now combine resistors in series by simply adding them, and we can prove this using the physics that we've actually learnt. Yeah? And we can also do this for the parallel one as well. So in a series circuit, the voltages are all added together to make the total voltage, yes, which we just learnt earlier on. So also due to Ohm's law, the current in the terminal times by the resistance in total is equal to I1 R1, yes, is equal to I2 plus R2 plus I3 times R3 over here. So all of them are going to be the same. And then we can see that because it's a series circuit, the currents are all the same, so all the I's are equal to each other. So therefore it becomes I RT is equal to I open bracket R1 plus R2 plus R3. They're all the same. We can cancel them all out, therefore recognizing that RT is equal to R1 plus R2 plus R3. Yes, I've also got a full YouTube video which I walk you through this in slow motion, so it's a bit more easy to understand than for me just to read out. Combining resistors in parallel, yes, now I've got another circuit where there's 3 resistors in parallel. We can recognize that the total current in is equal to total current out at the junction. IT is equal to I1 plus I2 plus I3, yes, at the junction. But they also obey Ohm's law as well. So VT divided by RT, yes, the voltage in total divided by resistance in total over here is equal to V1 over R1 plus V2 over R2 plus V3 over R3, all of them over here. Now, because the voltages are all the same, because don't forget the voltage in each loop is the same, yes, they're all the same voltages, so therefore we can say all the V's are the same, factorize it out, 1 over RT is equal to 1 over R1 plus 1 over R2 plus 1 over R3, and that's how we derive the formula when we are combining resistors in parallel. Potential dividers. Potential dividers are circuits which use resistors to split voltages. Okay, so as you can see on the left hand side over here, I've got a simple circuit with a power source VT, that's the voltage provided across the terminals. V1 is going to be the voltage dropped across resistor 1, and the V2 is going to be the voltage dropped across resistor 2. Right, so how on earth do we use potential dividers? Well, we can simply split that incoming voltage, so the voltage from the cell, into different amounts based upon the resistances in the circuit. So first of all, it looks better when I walk you through this problem. So let's say we were to calculate the voltage across resistor 1. How could we do it? Well, there is a formula which I'm going to prove right now. So number 1, first of all, resistor 1, first of all, it will obey Ohm's law. So therefore, the voltage V1 across it is equal to the current going through it times by the resistance of that resistor R1. So V1 is equal to I1 R1. Make sure that you're happy with that. Because it's a series circuit, recognize that the current everywhere will be the same. So the current going through the terminal is the same as the current going through the first resistor. Also, the current going through the second resistor, they're all the same over here. So IT is equal to I1 is equal to I2. All of them are the same. So now, we start off with V1 is equal to IT times by R1. Right, so how are we going to get a formula, in terms of the other resistor included within here? So right now the formula is IT times by R1, but how do we incorporate R2 into here? Well, if we were to draw a circuit, combine them both together, we recognize that when you combine them together, RT, the resistance in total, is obviously equal to R1 plus R2. So that's our next formula. So RT, resistance in total, is R1 plus R2. Due to Kirchhoff's first law, the voltage VT across the cell is going to be equal to, obviously, the voltage across the combined resistance RT, the resistance in total. They're both going to be the same. So we already know that the voltage across the terminal, VT, is equal to IT, the current going through the terminal, times by RT, the resistance in total. Yes, make sure you're happy with that. But we already said from before, resistance in total is equal to R1 plus R2, because we now substitute that back into here. Right, so the voltage across the terminal is equal to the current in the terminal times by, R1 plus R2. Yes, R1 plus R2. So just make sure that you're happy with that. So don't forget that's the current in total. Yes, the current in total. Then rearranging that to make the current the subject, IT is equal to VT divided by R1 plus R2. R1 plus R2, we just rearrange that. Now, if we take that initial formula, V1 is equal to IT times by R1. Yes, and then we replace the IT with what we've just worked out. So it becomes V1 is equal to VT R1 divided by R1 plus R2. So that's how you can actually work out the voltage across the resistor R1 by using that formula, just by you doing VT times by R1 divided by R1 plus R2. And obviously if I have n resistors in there, it changes because it becomes V1 is equal to VT R1 open bracket R1 plus R2 ... obviously R to the n, yes, at the bottom here. Just make sure that you're okay with that here. So that's how you could actually calculate the voltage dropped across one of the resistors based upon the other resistors in that series circuit, and that's going to be the use of the potential divider. If you don't like that, you can also look at potential dividers in terms of the splitting of the voltage in terms of the ratio. So over here I've got another circuit. I've got the voltage going in to be 12 volts, and then I've got V1 across here and V2. R1 is 100 ohms and R2 is 200 ohms. How will the voltage be split? Well, look, it's the ratio of the resistances. 100 ohms to 200 ohms is a 1:2 ratio split. Therefore, we're splitting that 12 volts into a 1:2 ratio. The first one will obviously take 4. Yes, 4 volts. The other one is 8 volts, because now it's split in that ratio 1:2. And obviously the 4 volts plus the 8 volts equals to 12 volts, when therefore makes all our mathematics work out. Internal resistance. Right, within every single power source and battery, inside it, there is actually a resistance within the power source itself. So internal resistance R, lowercase r, is going to be the resistance within inside the power source itself. Right, so as you can see, I've drawn a diagram and I've drawn that little arrow to show you what's actually inside. So let's say we have the cell, but inside it, there's actually, yes, there's another cell. So I know that sounds weird, but basically that is a source of voltage that's trying to come out, but there's a little resistor in there. Obviously, that's not an actual resistor, that's just a resistance within the power source itself. We're going to give it a lowercase r in terms of its symbol, and hopefully you can see that we're going to call the voltage that's trying to come out the EMF. Yeah, so the EMF, as you can see, the EMF stands for electromotive force, which is the voltage supplied to the external circuit when the current is zero. So when the current is zero, that is the amount of voltage you will get. The EMF will come out. VT we're going to define as the voltage across the whole terminal. So obviously if I put the voltmeter around the cell on one side and the other side over there, you can see that that will be the voltage in total coming out. So all VT, the voltage across the terminals. Now obviously the voltage across the terminals will be equal to the EMF E minus the voltage dropped over the internal resistance R. Yes, because obviously as current flows through it, yes, that internal resistance is going to take some of that voltage away. And that's why we're going to say it's equal to the EMF minus the voltage lost across R. So look at our formula, VT, the voltage across the terminal, is equal to the EMF minus the voltage lost. That is going to also obey the Ohm's law, so therefore we can replace the voltage lost with the current going through that internal resistance R. Make sure you're happy with our formula. VT is equal to E minus IR, and we've defined VT as the voltage across the terminals, R is the internal resistance, E is the EMF of the cell, and I is the current flowing through that circuit. Now, in a bit more detail, I've connected the power source to an external resistance capital R. So look at that circuit, it's now being connected to external resistance capital R. We're going to put a voltmeter across the terminals and a voltmeter across the external resistor capital R. Let's look at the mathematics behind it. Right, the voltage across the terminal due to Kirchhoff's second law will be equal to the voltage across the external resistor. They'll both be the same because obviously the voltage in is equal to the voltage out. So VT is going to be equal to VR. But obviously the external resistance will obey Ohm's law, so VR will also be equal to IR, where that means I times by capital R, not lowercase r, capital R. So then it becomes VR is obviously equal to IR, but you already know that VT is equal to VR, so VT is equal to IR. But from previous slide, we recognize that VT is also E minus IR, the EMF minus the current times by the internal resistance. Now equating them both together, the EMF minus the current times by the internal resistance is equal to the current times by the external resistance. E minus IR is equal to IR. Obviously, one's lowercase, one's capital. And therefore we can get another formula for the EMF. It's going to be equal to the current, open bracket, R plus little r, which is going to be, obviously we've factorized the I out over here. So the EMF is equal to the current times by the external resistance plus the internal resistance. How to find the internal resistance of a cell? First of all, you take your cell and you connect it to a load resistor, yes, an external resistance, R, capital R, connect it to an ammeter running back to the terminals over here. You put a voltmeter around the external resistor, yes, over here, VR. Now, VT, the voltage across this terminal, which we don't need because it will read the same as this one over here, is equal to VR due to Kirchhoff's law. VT is equal to E minus IR. VT is equal to E minus IR. The voltage across the external resistor R, yes, will therefore be equal to E minus IR because they're both the same. They're both the same. Now, as you increase this, don't forget there's an arrow going through it because it's going to be a variable. As you increase the external resistance R, don't forget, as you increase this, the current in the circuit will drop down. Look carefully. If the current in the circuit drops down, this value, I times by R, will get lower and lower because the internal resistance is constant. That won't change. The EMF won't change either. So this whole term will get lower. Therefore, VR will become higher. So VR increases. And by converse statement then, as the external resistance gets lower, there's greater current flow through it. If there's greater current flowing through it, what will happen is, don't forget, if this gets higher and higher, you're losing more then. Therefore, VR will decrease. So we end up with the following graph over here. We end up with a graph of voltage and current over here. And we can see that, yes, if we take our formula, VR is equal to E minus IR. I just spaced it out over here. And as I've shifted the minus IR backwards and put the EMF in front, and then I've just split them here, R and I, we can now link it to the equation of a straight line, y is equal to mx plus c. So as you can see, if I plot on the y-axis V, the voltage across the external resistance R, and on the x-axis the current over here, the gradient of the line is going to be equal to the negative of the internal resistance over here. And the EMF is equal to the y-intercept. Yes, so the gradient of this graph will be equal to minus the internal resistance of the cell. Drift velocity, I is equal to NAVE. Right, so first of all, let's consider the following bit of a wire. We have a wire here, it's a cylinder, there's loads of electrons inside it, and it's a cross-sectional area A of length L. We know that current is equal to Q divided by T, but also the amount of charge is equal to the number of free electrons times by the charge of each electron, because E is electron charge. So I is equal to NE divided by T. Now we're going to have a new term, it's going to be called eta. It looks like an N. It's going to be the charge carrier density. The charge carrier density is equal to the number of charge carriers per unit volume. So the number of charge carriers is going to be capital N, the volume is V. Therefore, we can then plug this into here. We're going to replace N with eta V. So I is equal to eta V E divided by T. So I is equal to eta V E divided by T. Don't forget, this is the number of charge carriers per unit volume. Its units are going to be per meter cubed, because obviously it's volume. But we also know that the volume is equal to length times by cross-sectional area, yes, for a cylinder. So L times by A. So we can now plug this into here, yes, replacing the volume over here with L times by A. The current is equal to eta, charge carrier density, times by the length of this, times by the cross-sectional area, times by E, the charge of one electron, divided by T over here. And then finally, if you know the electron has traveled a distance L divided by time, L divided by T is equal to V. So therefore, I is equal to eta A V E over here. And that's going to be our formula for the drift velocity. The current is equal to the charge carrier density times by the cross-sectional area times by the velocity of the electrons, the drift velocity of the electrons, times by the charge of the electron. And now we can talk about what happens to eta if you increase I. So obviously, if eta increases, if you put a greater amount of charged particles within here, yes, obviously we can see from the equation, and also that if there's loads more charged particles, there's a greater flow of current, so the charge flow increases. But this one's a bit strange here. If eta increases, the average velocity will actually decrease. Look at the formula. I is equal to eta AQV. Yes, you can see that if you were to rearrange that, eta and V are inversely proportional to each other. The reason why the velocity would actually decrease, if you put more and more charge carriers all the way inside here, what actually happens is they collide more often, and therefore the overall velocity decreases. Resistivity of a wire. The resistivity of a material is a measure of the amount of resistance of a material independent of the volume of the material itself. So it's a measure of its resistance independent of the volume. We'll derive it and then we can look at it in a bit more detail. So let's say we have two wires over here of different lengths, yes, but the same area. Hopefully you recognize that the greater the length of the wire, the greater the resistance. The reason why is because you've got more to pass through, yes? So therefore resistance is proportional to length. But what about if it was the same length but different area? Hopefully you can see that if you were to increase the area, the resistance drops down. Why? Because now it's easier for you to flow through it, because there's more space for you to flow through. It's like going through a 1 lane versus 5 lanes. It's much quicker because you can weave in and out to get there. Combine them both together, resistance is proportional to length, resistance is proportional to 1 over A. Combine them, R is proportional to L over A over here. Now, the constant of proportionality is the resistivity of the material. So R is equal to the resistivity over here. Now, in terms of the units, R is in ohms, length is in meters, the area is meters squared, so therefore the resistivity, the units is going to be ohm meter, are going to be the units of resistivity. And as we said earlier on, the resistivity of a material is a measure of the amount of resistance of a material independent of the volume. And as you can see, once again, we have the wire, and if you measure the diameter, you have to work out the area. Careful with this, it's pi r squared, obviously it's a circle, pi, but you've got the diameter d over 2 squared. Don't forget, therefore, it's equal to pi d squared over 4. The examples of different materials over here that I've put down just give you a bit of an idea that the resistivity, how it changes. So obviously, silver, copper, lead, you can see that it's got very low resistivity, but look, you can see that glass and rubber, obviously they're not great at conducting, so therefore they have the very high values of resistivity. How to work at the resistivity of a wire experiment. So first of all, you're going to have the following bits of equipment. You're going to have the wire of length L, You're going to have a voltmeter, an ammeter, and a power supply over here. All you're going to do is change the length of the wire and record values of the voltage going through it and the current. Okay. And obviously measure the diameter as well. So we're going to measure the diameter of the wire at different lengths because of the non-uniformity of the wire. And then we're going to record the values of the voltage and current using the voltmeter and the ammeter. Then we're going to repeat for different lengths of the wire. We're going to calculate the resistance using R is equal to V divided by I, because at each point we're going to get a value of V and I, and therefore we're going to calculate R by using Ohm's law. Then we're going to plot a graph of R against L. Don't forget, R is on the y-axis, L is on the x-axis. Now, to determine the gradient of the graph, we're going to then plot the graph and work out the gradient, and the resistivity of the wire will be given by the gradient times by the cross-sectional area. And I'll explain how I got this in a minute. So, first of all, the formula is R is equal to rho L divided by A. And here's your table of results over here. We measured V and I over there. We calculated R using Ohm's law. But then look, if I was to plot on the y-axis R and the x-axis L, we can link it to the equation of a straight line. Y is equal to mx plus c. So as you can clearly see, on the y-axis, if I've got R, x-axis I've got L, the gradient of the line is equal to rho divided by A. And therefore, rearranging it then, the resistivity is equal to the gradient of this graph. So you plot the graph, you work at the gradient, and then you times by A. And that's it, guys, for another session of Ceerazzledazzle Physics. I know this was a long video, guys, so make sure you pause it at certain points. And obviously, you don't understand something, comment, and I'll be able to obviously respond back to you. But make your own notes. Don't forget, pen and pad is still the best way to learn. I know everyone thinks that, you can just buy a revision guide. No, but when you write it down, obviously, you're going to retain it more. So just make sure that you're putting all the effort in. Don't forget, this is one of my videos and a series of videos which I'm making on the entire A-level. So I will have all the A-level revision videos one by one, and finally I will make an entire video based upon the entire theory of the A-level all in one video, so therefore you don't have to look anywhere else, it will all be there. And obviously if you want me to walk you through stuff in depth, you have to check out my YouTube channel and obviously browse the video that you need, because in this video it's a revision video. I'm just going through stuff quite quickly just to help you before an assessment, but if you want to learn in depth, you need to obviously spend the time going through the material yourself. Okay, and that's it. Ciao, ciao, goodbye, and make sure you share my content and keep it as free as possible. Like and subscribe. Ciao, ciao, and goodbye. If you're looking for additional resources, including my own revision notes or academic tuition, get in contact via my website or drop me a comment.